So yeah, we need to talk about inhibitors. So let's go back to page 75. Thank you for keeping me on track. I appreciate that. So there is a seventh factor that affects reaction rates. We haven't talked about it yet, but it is called an inhibitor. And an inhibitor is basically like an anti-catalyst. So tell your partner how a catalyst affects the reaction rate. Alrighty. A catalyst affects the rate by providing an oh, I heard the word alternate. Pathway or path. With a lower, and I'm just going to put EA because I'm writing up at the top of the page and we don't have a lot of room. Now, that would get you 2 marks if this were a 2-mark question, right? 1 mark here, 1 mark here. Now, what if it were a 3-mark question? What could you add to that in terms of collision theory? Whoa. Chat with your neighbor about that. What could you add in terms of collision theory to get a 3rd mark? Oh, what? Oh, like that? There, yeah. What else do we need to add if it's a 3-mark question? And it says talk about collision theory. Yes, therefore, a larger percent of collisions, and that would be worth 0.5. Yes, have sufficient energy to be successful. And that would be your other 0.5 marks. Now you've sort of covered everything. Yes?
Please excuse the interruption. Could we please have one student from every classroom down to room 106 to pick up the fruit and veggies? One student from every classroom, please go down to room 106 to pick up the fruit and veggies. Thank you.
I'm glad it was this block, my last block of the day. Nobody wanted to go. I'm like, I would like some fruit. They're like, no, fine. Okay. So that's what a catalyst is. Now, an inhibitor is like an anti-catalyst. So based on what a catalyst is, what would you say that an inhibitor does?
So it's fine with alternate reaction paths. However, it would, instead of lowering the reaction energy, the activation energy, increase the activation energy.
Exactly. Okay. Yes. Okay, so the anti-catalyst, it will increase the rate by providing an alternate pathway with a lower activation energy. Usually it does that by, if this is my reactant, okay, actually, if these are my two reactants, okay, and they want to react with each other, the inhibitor will usually bind to this one, right? And then if this one, it's not going to get there, right? So what would have to happen is it would have to collide with a lot more energy to knock that off, right? And then you could get a reaction. The inhibitors are not usually very sophisticated. They're usually like, I grab on so you can't get at it, okay? And that's it. So an inhibitor increases the activation energy, usually by binding to a reactant molecule, making it difficult for the other reactants. I should just say for the reactants, not the other reactants, for the reactants to collide effectively. I'm going to put a fix there. Fix. Okay, so we will have a smaller fraction of collisions then that have sufficient energy either to react or to form the activated complex. Many food preservatives are inhibitors. Food. Do you want your food to rot? Oh. So they'll bind to the food and they'll prevent things from reacting, okay? So here is our with inhibitor. Here's our no inhibitor. That's basically it. You can label the axis, I don't know, why did I even write this? The x-axis progressive reaction, you could write it as you'll see this sometimes, reaction coordinate. I don't even know what that means. I don't know why they do that, but if you see it, just know, I wouldn't expect you to write it, but just know that that's what it means. You could write reaction proceeds. Or reaction occurs. Any of those are okay. And the y-axis should be labeled with potential energy in kilojoules per mole. Okay, and that's it for that. So now we will bop along to reaction mechanisms. Now I would like you to imagine that I have three particles and that in order to react, they need to collide like this. Okay, that is the geometry with which they need to collide. Are you with me? No, stop looking for your pages. Just look here. I'll tell you what page we're on in a second. Don't worry. Can you imagine what is the probability that these particles will collide like this? Very low, yes? And what if I had a fourth particle and it had to collide exactly like that? Even lower. So every time I add a particle, the probability of the correct orientation, and you'd have to have sufficient energy, the probability goes down, and it goes down quite a lot. So any reaction that has more than 2 reactant molecules will have a reaction mechanism involving more than 1 step. So what the heck is a reaction mechanism? Well, it involves more than 1 step, so it is a step-by-step process. Step 1, step 2, step 3, that reactant molecules undergo in order to produce the eventual products. Okay, so here is our definition. Okay. They won't just bump into each other. So what will actually happen is you'll have these 2 guys bump into each other, and they'll be like, oh, I'm going to form that. Oh, here we go. I can do that. There. Oh, we got that. And now we'll have the 3rd thing then collide with this one. And then do, you know what I mean? Like they'll eventually get to products. We'll do it with something a little less unwieldy than pens. Okay, we'll just do it with some diagrams and stuff here. Okay, and that is because the probability of more than 2 colliding. What does simultaneously mean? That's a big long word. At the same time, yes. So if you are learning English for the first time, maybe it's only been a few years, simultaneously is a big long word. That means at the same time. Although it's really funny, the words that give people trouble, when they're learning English, sometimes it's not things I would predict, like the word lump, that is problematic. And I've noticed that since I started teaching. I talked about a lump of coal, and everyone would ask, what's a lump? I'd be like, oh, didn't expect that one. Anyway. So simultaneously with sufficient energy and the correct geometry is extremely small. Therefore, to avoid this, we set up a series of steps. Each step involves only 2 molecules. So here we have our overall reaction. 4 HBr plus O2 gives 2 H2O plus 2 Br2. Well, we have 4 HBRs and we have 1 O2, so that gives us a total of 5 reactant molecules. So we are now in the realm of very, very, very improbable that they will collide with one another correctly and with enough energy. So instead, we get several 2-particle collisions, one at a time. So we take one of the HBRs and we put it together with one of the O2s, and they collide and they make this temporary molecule, HOOBr, okay? And we can call that a Huber molecule, just because I think that's kind of fun. Okay, so we make Huber. And Huber is not a product, right? If we remember, what are our products? Our products are water and bromine. So we've not yet made any water or bromine, we've just made Huber. Now, quite frankly, I don't actually want any Huber molecules because those are not my products. So this guy actually now goes and reacts, so we get rid of it in the next step. Okay, so the Huber reacts with a second HBr, and we get 2 Hobers. Okay, Hober. Now we don't want any Hobers either because our products are not actually Hobers. So each of these Hobers, one at a time, okay, one of them will react with an HBr. We will get H2O and Br2. That will have to happen twice because we have two of the Hobers, okay? So this is a 3-step process, 1, 2, 3. And somebody did some experiments and determined that the first step was slow, okay? That means whenever we have a reaction mechanism, one of the steps is going to be the slowest step. We labeled that slowest step as slow. Everything else gets labeled as fast. Okay, so there's one slow step, everything else is labeled as fast because we're only really concerned about the slowest step. So the slowest, oh my God, I can't write. All the other steps. Get labeled fast. Just means they're faster than the slowest step. What we labeled them? Because the rate is only dependent on the slowest step, and we'll talk about why in a minute or two. So as long as you know the rate of the slowest step, you know the rate of the whole reaction. Okay? So an elementary process is just a name for an individual step. Okay? So step 1 would be an elementary process. Step 2 would be an elementary process. Yes?
How did step 2 reactions become the product?
How did the Huber plus the HBr become 2 Hobers? Well, I've got 2 H's. Yeah? I got 2 H's. I got 2 O's. 2 O's. And I got a BR and I got a BR and I got 2.
That's what we don't have there. On step 1.
We wrote out what? Oh, well, you know what? You're going to be given a reaction mechanism. You're not going to be expected to, you won't be expected to come up with the steps. You'll be given it, or you'll be given like step 1, 2, and 3 will be a blank, and you'll be given the overall, and you'll have to figure out the third, but I will show you how to do that. So don't worry about that just yet. Okay? Yeah, you're not going to have to come up with those formulas yourself. Okay? Okay, elementary process, any individual step in a reaction mechanism, they are 2 particle collisions. All right, so the above reaction mechanism, this whole thing all together, what's it called? The reaction mechanism. So this reaction mechanism has 3 steps. It has 3 elementary processes. Now I circled the Huber and I boxed the Hober because they are important, because in any reaction mechanism, you will have things that get produced but aren't actually products. So they need to get used up again. Okay? Those things are going to be called reaction intermediates because they appear as an intermediate step. Yes? So a reaction intermediate is like the Huber and the Hober So it is a substance which is produced in one step. So first it's produced. And then later it gets used up in a subsequent step. The reason I put the word subsequent in there is because you might hear that and you might say, what the heck is subsequent? Yes? The word subsequent means later. So sequence, the order of things, subsequent comes after, okay? Not that you need to use this word, but if you come across it, I don't want you going, what? What is that? So first, the reaction intermediate is produced, and then second, it's used up. So where does it show up first? Does it show up first in the reactants, or does it show up first in the products? First, it shows up in the products, or actually I should say on the product side. And second, it shows up on the reactants side. We're going to look at something later that appears first in the reactants and then comes out later in the products, so we don't want to get it confused, okay? So you could make it in step 1 and use it up in step 2. You could make it in step 1 and use it up in step 3, like it could wait a step to get used, or you could make it in step 2 and use it up in step 3. What you couldn't do is make it in step 3 and use it up in step 1, because that doesn't make sense, okay? So we've already done this. We have circled the reaction intermediates here. We have our Huber and we have our Hobers. Okay, there we go. Now, on our next page, if we have circled these and we add them up, it's very much like adding up mathematical equations. You know how you add mathematical equations and you cancel things that are on opposite sides and you add up things that are on the same side? It's exactly like that. So we see a Huber on the right-hand side and there is a Huber on the left-hand side, and they cancel out. If you have something on the left and on the right, what will they do? They will cancel out. Okay, so the Huber cancels out, the Hober cancels out, and we have 2 Hobers here, but fortunately, we also have 2 Hobers there, right? Because this 2, we're multiplying the whole thing by 2 because we need to get rid of both Hober molecules, okay? So those cancel out, and what are we left with? We are left with 1, 2, and then we've got a 2 times HBr, so that's 1, 2, 3, 4 HBrs, yes? So we got 4 HBrs. And then we have an O2. Okay, just 1 O2. Oh, there it is. Okay. And on the right-hand side, we have a water, but we also have this 2 that's multiplying the entire equation. So we have 2 waters. And bromine. Where'd it go? There it is. Bromine. Again, we have two of them because we're multiplying that entire equation. So we have 2 bromine. And look what we ended up with. That is our overall reaction. So when you add up the steps of a reaction mechanism, you will always end up with the overall reaction. Okay? Now, sometimes people get confused between an intermediate and an activated complex. Okay, so we're going to make sure that you don't. An intermediate is we're going to put product in quotes because it's not really a product because it gets used up later. It doesn't actually stay produced. It's a product in one of the steps, but then it gets used as a reactant in a later step. So it's neither a reactant nor a product, but it does show up on the reactant side and on the product side. And if we write out all the steps, the reaction intermediate is written in reaction mechanism equations. Okay, so you will see it in the steps. Now, let's just remind ourselves, we went through this yesterday, so I'm not going to make you tell each other again, but an activated complex is a short-lived, high potential energy, unstable. Do you remember those 3? Arrangement of atoms, or you could say chemical species that occurs when reactant molecules collide and bonds are broken, or you could say collide successfully, okay? When the new bonds form, it either becomes the final product or it will become the reaction intermediate if it's a step, okay? If it's an earlier step. We do not write them in the reaction mechanism equation. So we write it. Do not write it. And the reason for that is, where does the activated complex occur? It occurs during the reaction, right? Activated complexes exist during the reaction process. When reactants are turning into either reaction intermediates or products. So if we take a look at our reaction mechanism here, we can see here's step 1, okay? And look where the activated complex is. Remember, we can represent it with a star. There is our activated complex. It's taking place during the reaction. So we can write it above the reaction arrow. So this is very unstable. So we don't even see it in there at all. And then we get this intermediate. Okay, so our reaction intermediate is here. So the reaction intermediates actually show up. They're not as stable as the reactants or products usually, but they are more stable than an activated complex. Yes? We don't, but you can put a star above the arrow should you just so desire. Okay? So, like we can, but the thing is, we put it there so that you know it's there while we're learning about it. But when we've finished learning about it, you can just be like, yeah, I know it's there, but I'm never going to write it there because that's just weird. Yeah? That makes sense? Cool. Yeah. Good question. All right. So our reaction intermediates do appear in the equation. Normally, we would not write these little stars. Okay, like Marva was asking, normally we don't. We're just sort of putting them there so you know the difference between an activated complex and a reaction intermediate. Should you need to write the formula of an activated complex, you simply mash all the atoms together into one formula and put a star on it, and the order doesn't matter. But I'm not going to ask you to do that, so don't worry about it. Okay? Okay. So for example, here is step 2, okay, of the reaction mechanism, and we're just going to write some possible things that we could write for the activated complex. The activated complex needs to contain 2 H's, 2 O's, and 2 Br's. So you could write it as H2O2Br2. You could write it as O2H2Br2, or H2Br2O2, or O2Br2H2, or like this. But like I said, I'm not going to ask you to do that, so don't worry about it. All right? It's more if it comes up in an example and you see it, you understand where it came from. Okay? Now, Hebden was ever so kind as to kind of draw what this might look like for us. Okay, so here's step 1. We have our HBr and our O2, and bam, they hit each other, and what has happened to those bonds? The bonds have broken, and we also have new bonds that are sort of starting maybe to form but have not formed yet. Yes? So these are broken bonds. Yes? And so we've broken this bond, we've broken this bond, and now we're starting to have some new bonds forming. So these new bonds formed, and now we have a single bond here rather than a double bond that we started with. Are you going to have to be able to write that? No, you will not have to figure it out. Okay, it's just to give you a picture of how it happens. All right, but you do not need to be able to draw any of that. Reaction intermediates, they are more stable than the activated complex because bonded structures, things that are bonded, tend to be more stable, right? Bond formation takes us to a lower potential energy. We release energy. Unbonded are less stable. So our activated complex is less stable. Therefore, the activated complex will have a higher potential energy than the reaction intermediates. Hooray! Should you want to see all the other steps with their activated complexes, you can look on page 27 of Hebden. I did not think it was worth it since we won't be doing them. Okay? All right. Now remember, we said the slowest step is special, right? So special, we just call it the slow step. And in fact, we have a better name for it, is called the rate determining step. That is our slowest step, and it is labeled slow. What is wrong with this pen? There we go. Say, oh. Okay? A reaction cannot go faster than the slowest step. And that's why it determines the rate. That's why it's the rate determining step. Okay, the slowest step, if the slowest step goes, let's just use speeds, like, we're traveling along a highway. Okay, not a highway because these are going to be slow speeds. But we're traveling along a road. If one thing is going at 5 kilometers an hour and one is going at 10 kilometers an hour and the other is going at 30 kilometers an hour, we can only go at 5 kilometers an hour. Now, the road analogy is actually kind of crappy because it doesn't really explain things. So I'm going to do another analogy, but I need some volunteers to come and help me. And I'm going to turn this off so you don't get blinded. And I need 3 people to come up here. Anyone want to come up?
Sure.
Excellent. Perfect. Thank you, Caden. Anyone else? Thank you, thank you, thank you, thank you. Achin. I need one more person. I need one more person. I can't do it without another person. Oh, thank you, Jacob. Perfect. And you know what? These guys all get a bonus mark on their quiz. Don't you wish you had volunteered? Oh, yes, you do. I'm so sorry. You lost your chance to get a bonus mark on the quiz. Oh, so sad. All right. Thank you so much. So what we're going to do is we are going to pretend we are at a restaurant, okay? And we are washing the dishes, okay? So we have Caden here, who is the dishwasher. Okay, we have Jacob, who is the dish dryer. And then we have Achin, who is the dish putter awayer. I know there's going to be a better word than that, but I don't know what it is. So you put away the dishes. Now, Caden is a perfectionist, okay? He really wants that dish to be clean. He's really worried about food safety, right? So Caden, when you get the dish, which is actually a pencil, okay, you're going to scrub it and work at it and make sure it is completely clean before you pass it on to Jacob. Okay, now, Jacob is a disgruntled employee. His boss has been mean to him. He doesn't get paid enough. Like, it's just life sucks for Jacob. So he doesn't feel like he's getting paid enough to do a good job. He basically just dumps it in the water and passes it on to Achin, who is also a disgruntled employee, and you're just going to put it on the desk beside you, and that's putting away, okay? You can only hold one pencil at a time. And as soon as I give you this one, then I will just get ready for another one when you are ready for it. Okay, so here we go. Yes, we're doing work here. Mm-hmm. So who's the rate determining step? Who's determining how fast this process can go? Caden, because he is the slowest step. Shall we change our roles? Okay, we're going to change our roles. You're still going to be the washer, the dryer, and the putter away. But now, Caden, you are disgruntled. I'm so sorry. Okay, Jacob, you are also disgruntled. And Achin, you are the perfectionist. You are going to go and find the perfect place over on that counter to go put away the dishes, okay? Because that's where they really belong. All right? There you go.
Spit down.
And remember, you cannot get rid of it until you've got someone to pass it along to. Who's who's determining the rate this time? Action is determining the rate because we cannot go any faster because the intermediates can't go until we've done that. Thank you guys so much. And I'm gonna write down right now that you get a bonus mark on your quizzes so I don't forget. Thank you so much.
Go ahead and go.
Oh yeah, sure, thank you. If you guys want paper towels to like put those on, you can put them down on those. Okay, we've got like snap peas. All right, so we got +1 pay down, +1 action, and +1 Jacob. Okay, so if we go on to our next page, page 86, you can actually see we have a little bit of a different picture here. This is a different analogy. If your first step has the smallest capacity, you cannot fill it any faster than you can with that first funnel. That funnel will overflow, right? And it doesn't matter where you put the smaller funnel, you cannot fill faster than it can go through the smaller funnel. So that's another analogy. But if you understand it, that's fantastic. I hope that made it clear to you. If you don't, you can always memorize the fact that the slowest step is the rate determining step, and you cannot go any faster. It determines the rate. Okay? The speed of the overall reaction is the speed of the rate determining step. We've already talked about this. The rate determining step is always labeled as being slow. All the other steps are labeled as being fast. Therefore, only one step will be labeled slow. All the rest will be labeled fast. Here is a proposed 3-step mechanism for the reaction of Cl2 and CHCl3. If I was to give you this on a quiz and I said, please label the speed of that third step, tell your partner what you would label the speed of that third step. Fast, because we can only ever have one slow step. Okay, circle any reaction intermediates. So if you could please circle any reaction intermediates. And then once you've done that, you're going to add up the reactions to give the overall reaction. So we're working through these little steps here, okay? So give those a try. Once you have answered the questions, check with your partner and see if they get the same thing as you do.
Like the actual like products are just. So when it comes to the product, CCL for that. Oh.
Did you guys get those ones? Are those your reaction intermediates? And then what did you do with them when you want to write the overall reaction? To write the overall reaction, you add up the steps. So what do you need to do with your intermediates? They are on the right-hand side and then they are on the left-hand side. What do we do with things that are on the right and the left? We cancel them. Bye-bye. Okay, there's 2 chlorines. It's okay that one gets used in step 2 and one gets used in step 3. So once those are canceled out, if you've not yet written your overall reaction, please write the overall reaction. So our reactants, Cl2 gas is a reactant that comes in step 1. CHCl3 is a reactant, comes in step 2. HCl is a product. And CCl4 is the product. So if you were to write the products of the overall reaction, it would be HCl plus CCl4. I don't know if it's worthwhile writing the activated complex for step 2, but if you had to, CHCl4 star would do. Okay, but I'm not going to make you do that. So that's it. That's it for that. We feel pretty good about that. Okay. There's a solution there, blah, blah, blah. Now we are going to try this one. This is a little trickier because we are going to solve for step 3. Because we have the following reaction. has a 3-step mechanism. So this, what is this? This is the overall, okay? When it says this reaction occurs by a 3-step mechanism, that means that this is the overall reaction. So we have already added it up. Now, often, and this is a little tricky, they will give you the overall reaction like at the top. And normally, what do we like to do? We like to add things up as we go downwards. So wouldn't it be nice if we put the 2A4 plus at the bottom, right? And the B plus goes to 2A3 plus B3 plus. So what we've done is we've written the overall at the bottom. Then what we're going to do is we're going to say, what do we actually have that we want to keep for the overall reaction? Well, for the overall reaction, we need to keep 2A4 pluses. Do we have 2A4 pluses? We do. We have one here, and we have one here. Okay. So we don't need to do anything with those A4 pluses. We just leave them alone because we're going to want them to add downwards. Do we have a B plus in the reactants? No. So where does B plus have to appear? In the reactants in step 3, because it's not in step 1, it's not in step 2, it has to appear in step 3. So what you do is you start by taking a look at the overall reaction, and maybe I'm going to make this one like a little circly, like a little cloud, okay? Do I have 2A3 pluses in the products? Yes, I do. Oh, look at that. They're right here and here. That's terrible. I've made a big mess of it, but that's okay. And I also want to have a what color do I want? Let's make it light green. I also want to have a B3 plus. Do I have a B3 plus? No, so I'm going to write B3 plus in the products. That's a terrible pen. B3 plus, there we go. Okay. Now, of course, I need an arrow here. So now I've dealt with everything that I need to have. Now I need to make sure that everything else cancels out. Does C2 plus cancel out anywhere? No. So where would I need to put it in order to make it cancel out in the final step, step 3? It's on the left, so we need to put it on the right. So over here, we're going to put C2 plus. So that's going to cancel out now. We also want, we can say, I've got a C3 plus. Does C3 plus cancel out? Oh, yes, it does. So do I need to do anything with C3 plus? No, because it's going to cancel already. And finally, how about C4 plus? Oh, it doesn't cancel out, so I need to put it over here so that it will cancel out. C4 plus. Okay, so that is how that works. So basically, The easiest way to do it is to start with all the things in the overall reaction, make sure that you have them, and then make sure everything else cancels out. And then the second is make sure everything cancels out. Everything that needs to cancels out. Okay, is that the end of this one? No, there's exercises, good. Okay, so you guys are going to do this stuff, and look, what's question 9? Do Hebden, page 28, number 46, 49, and 50 to 52. Where would you find Hebden? Either you have it at home, or it's back there, or actually it is online as well. Okay, so your Hebden should probably be at home. Just take it home and leave it there. But if you are at school, and let's say it's tomorrow morning during Flex and you want to work on those, at the back of the classroom on that bookshelf, there are extra copies. Okay? So do those for homework. And I think we are we good? What time does this class end? 10 minutes from now? Why don't you just start on these? Yeah? We never get time just to work. Oh, that would be shocking. Oh. Yes. There? Yeah. It's all right. Yes, 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 yes. Let me grab that for you. There you go.